Hi, everyone. My name is Sandeep, and today we're going to talk about a failure case. So let's start. My name is Sandeep. I work as a solution architect at Anstack. At Anstack, we build serverless and AI applications. So you can reach out to me on any of these handles. So this is how it started. One of my colleagues sent a message in our Slack channel telling there's a hackathon, why don't you give it a shot? So we were like, it's about gaming, so why not give it a shot? And about the game, so Valorant is an online multiplayer game, and you have 5-player team. You have 13 rounds to win the game, and you have about 28 agents. So these agents are special characters that you can choose. Each character has a different power. So when you create the team, it's about using all these special powers together and provide a strategy. And we have about 12 maps. Each map vary in the kind of location, the kind of sneak spots that are there, what kind of tactics you're going to use. So all of it depends on the agent combination and also the kind of map you're playing. So we were given a script from the Valorant team. All we had to do was run the script, and we get the data into our systems. But when we ran the script, it took a very long time, and all our laptops crashed. Luckily, it was in an S3 bucket, so we just did an S3 sync to get all the data to our S3 bucket, and this is what we ended up with. So the data we were given were about 7,500 game files from the Valorant team, which is spread across 3 different leagues or 3 different tournaments, and it is for 3 different years of gameplay. The total size of this was 100 GB. So we wanted to see what is there in these files. So when we downloaded some of these files into our laptop and tried to extract what is there, even then our VS Code was crashing because these files varied anywhere from 200 MB to 800 MB of pure JSON data. So that's when we started using Amazon Lightsail. So Amazon Lightsail is an easy to use, easy to in a manner. So you get all these extracted or abstracted resources like a Node.js server or a Django server or anything like that. So what we did is we ran the uncompressed script into the Lightsail, and then we connected it through our VS Code, through our remote SSH, and it gives you the wonderful dev experience. It looks like you're working from your laptop, but you're actually running the scripts on the server. So after the uncompression was done, the total size arrived to 800 GB. Now the question is, what is there in these files? So what we started doing is just a JSON file, right? So we started splitting it up based on what are the keys that are available. And then we found all this information. Everything that a player does in the game is recorded in these files. How much ammunition you have, what speed you're running, if you're jumping, what is your coordinates, where are you landing, whom did you kill, how many times you got killed, and if you have used any special abilities, who won the game. Every single thing that is required for this game is available in these files. So once we started segmenting this data, we started recording on what is there in these files and what metrics we can use to derive or create a team of 5 players. One thing we quickly realized is the volume is not equal to the data. Even though we had 800 GB of data, once we started processing it, there was a lot of unwanted information that was there, and we started deriving these few metrics that are helpful for us to identify the best set of players. What we ended up with is creating 6 to 10 different data sets. These were specific to the characters that were being played, specific to the map that was being played with, and what are the player characteristics or the player statistics. So this had cumulated information on one player, how many games they have played, how many kills they have done, what is their combat score, and all relevant information on these kinds of metrics. Now that the data was ready, the question was, how do we use it? We cannot put it directly into an LLM because, again, it's a large set of data. The LLMs will not be able to process this information. That's when we thought we would give vectorization a shot. And we started doing that with Amazon Bedrock's knowledge base. So knowledge base is a very easy way for us to spin up a vector database and get connected to it. It also comes in with an inbuilt chatbot, so it's easy for you to see how your vectors are performing, how your queries are performing, and then you can fine-tune it based on that. The main thing about using a vector database is the chunking strategy. So first, we started off with default chunking. So default chunking is basically taking the entire JSON file and then it splits them into 300 tokens each, and then stores them as a vector record in the database. For the vector database, we used OpenSearch. Again, that's a very easy to create resource from the knowledge base. So these tokens that were stored, each of them is a separate record in the vector database. But when we do it like this, what happened was the JSON file containing all the information is now split up, and it did not make sense at all. So one player's information is now overlapping the next player's information, so none of it made any sense. When we ran queries over it, we did not get any output. Then we started to use something called as no chunking strategy. So instead of having one single file containing all the player information, we split up these files. Each player had their own file with their own metrics, and that becomes a vector record in the database. Now with this, we were able to see some good results. This is the kind of responses we got. So we used Claude 3.5 to see what kind of responses we are getting. And when we ask something like create a team of 5 players, it is now calling the vector database and getting the information out. So here we are asking it specifically to get the players based on the combat score. But this data is not correct. All the combat scores, there are players who have had better combat scores, and it just randomly selected 5 players in the lot. And this happened every single time. And if we did not specify combat score and we asked a generic question like create a team of 5 players, it never gave any valuable results to us. That's when we realized that this is not going to work out. And then we got into why this is not working out. So this is a sample of the JSON that we were storing in these databases. Now, all this information is spread across different characteristics of the data, right? So you have assists, you have damage, you have kills, you have the number of games won. Each of them are a different dimension or a different characteristics of the data. When you put all of them together into a vector space, all this information is now spread out, and there's no relevance between what is happening. We know that assist is something that you do, and combat score is something that is generated by the system. But the vectorization process removes all this context from it and just stores it as raw data, which does not make any sense when we are trying to query it back. The other problem that is there with vector databases is the number problem. So we know that 5, 10, and 15 are multiples of 5, but to an LLM or to a vector, these are basically just numbers that are just closer to each other. To a vector, probably 5 and 15 are more closer to each other, and 10 is in a different dimension space altogether. So when you put vectors which are having a lot of numerical value in them, they lose their mathematical value out of it. So you have to be really careful while doing this part. So the next question is, now that we know vectorization is not working, how do we let an AI decide who are the best players? The simplest thing to do is just to write a Python script which is going to tell, like, take these 5 metrics, accumulate them, find the average, and so on, right? But that's not something that we wanted to do. We wanted to make sure that the AI is able to understand that 10 metrics are available, and then it needs to use all these 10 metrics in its space to get the best information out. That's when we started experimenting or implemented function calling. Function calling is nothing but your agentic calling. So again, Bedrock has builders which are agents. Now, this makes it simple for you to create agents. It's just a 2-step process. So you start off with giving an instruction to the agent. Here you tell how the agent needs to react based on the kind of question that you're getting in. So what we asked it to do is select the best characters for each map, characters or agents, and then for each of those characters, select the best player who has played them across the league. And from this information, shortlist 5 players who will be able to work as a team. Now, after you get these 5 players, assign them to each map. And when you assign them, also tell what character they have to play as. So this is all that we did, all that we asked the LLM to do. And at the end of it, we also asked it to create a strategy. So in each map, how these players need to play. Who's going to attack first, who's going to defend, who's going to be a healer, all this information in one single prompt. And the other part that we did is we used action groups. So we created one action group called ESQuery. And what it basically does is we have a Lambda function behind the action group. This Lambda function then queries an OpenSearch table. All the information or all the data sets that we just discussed about is now stored in the OpenSearch database. The Bedrock is designed in a way that it is going to call the Lambda every time it needs information. It is going to generate an ES query and send it to the Lambda. The Lambda is then going to call the OpenSearch with the actual query, get the data out, and send it back to Bedrock. Now, when we did this, we got wonderful results. So in this example, you can see that it's not just taking combat score into the picture. It's also taking how many times the inventory was used, how effective that person was, how many times the entry frag was done, basically how aggressive that player is. And many other metrics are taken into consideration. So this is a holistic report on how it works or how beautifully it works. But then this worked only once in 20 or 30 iterations, or 20 or 30 times that we tried it. Then we realized the hiccups that were there in this situation. So first thing is the cognitive overload. So basically, we are just asking the LLM to do too many things in one single prompt. All the things that you saw in the graph are just too much. It gets a lot of data. It gets confused on what player needs to do or what metrics it needs to take from which player. The other problems that we had is the Lambda that is sending the response back to the LLM had a limitation that it cannot send more than 25 KB of data. And anytime that happened, the LLM executions failed. The next problem we had is there were too many function calls. Every time the LLM tried to query the ES, there were sometimes that there were 30 or more executions that happened without the LLM trying to triage into who the players are. Now, the ES queries are primarily dependent on the kind of data set that is there. So if you're running any aggregation queries on top of it, it needs to be, you need to make sure that these follow the kind of data that you have already stored. The last problem that we faced is something called as a frozen LLM. So in these cases, the LLM just got stuck. It just timed out. There were no function calls. There were no log traces of anything happening in the LLM, just that the execution stopped. So all this happened, and this was just 2 days before the submission of the project. And then we wanted to see how we can get this done in such a short time. That's when we tried with something called as multi-stage flows. So since we are very fond of serverless, we thought we'll just use a step function to get all of this done. So instead of one single LLM doing all these things, we split it up into different LLMs and then orchestrated everything using a step function. And then we use lambdas in between to cache the responses, store them in the DynamoDB. Because at the end of the day, we also had to build a chatbot to which you can ask queries like why this player was chosen or what is his strategy, and it needs to be able to respond to it. It worked until everything had to work together. Each of these pieces individually were working great, but the final summarization and selecting those 5 players never worked out. So finally, since it never selected 5 players, we were not able to submit it. We tried until the last 10 minutes, but then at that point, we just gave up. And then when we were preparing for this presentation, we redid the entire thing to take some screenshots. And that's when I wanted screenshots of things failing, but it never failed. And then we realized one very simple logic is that don't teach an LLM what it already knows. The difference between the prompt that we used before to now is one simple thing. Previously, we were telling the LLM how it needs to think, how it needs to select the players per map, per characters. This prompt had none of that information. It just said, select 5 players for a Valorant, or not even 5 players. Create a team for the Valorant team. And that's it. And we gave the schema of the OpenSearch, and it understood from all its previous training that Valorant is a game, and it needs to have 5 players, and for what map, what kind of aggression style, what kind of characteristics it needs to have. All that information was already available. All we were doing is retraining the LLM to do something out of its thought. And last, when we got this Slack message, we thought it's going to be a simple project. It's going to be like a weekend project where we sit for a week and it's done. And it was not easy at all. That's it from my side. Thank you for joining the session. If you have any questions, do let me know.